This is Chapter 2, Pre-Class Lecture, Part 3. And so in Part 2 of our lecture, we introduced the concept of a limiting reactant. It is the reactant that gets used up, or in other words, is consumed completely during the reaction process. The other reactant can be termed the excess reactant because it is not completely used up during the course of the chemical reaction, and therefore there'll be some of that excess reactant left over. And so now we're going to expand on the concepts of limiting reactant and excess reactant by introducing two new terms, theoretical yield and percent yield. So to explain the concepts of theoretical yield and percent yield, and also the process of how to go about determining which reactant is the limiting reactant and which reactant is the excess reactant, we're going to take a look at a specific chemical reaction involving the synthesis of aspirin. Aspirin is the product, is actually one of the products. The proper name for aspirin being the common name, the proper chemical name for aspirin is acetyl salicylic acid. Aspirin, or acetyl salicylic acid, is produced when you react salicylic acid with acetic anhydride. To make the reaction go fast, a strong acid, such as sulfuric acid, is also added to act as a catalyst. The role of a catalyst in a chemical reaction is to speed up that chemical reaction. Some reactions will happen, but will happen very, very slowly without a catalyst. And so if you want to watch a little video on the synthesis of aspirin, you can click on that link in your notes, and then you can watch the little short 9-minute video that demonstrates the synthesis of aspirin. And so the salicylic acid reactant, as you can see, is a solid powder. And so the 3 grams of that solid salicylic acid is measured out using a balance, of course, to make sure you've got exactly 3 grams. And to the 3 grams of salicylic acid, you're going to add the other reactant, which is an aqueous solution. An aqueous solution is a homogeneous mixture of a solid chemical compound that's been dissolved in water. So acetic anhydride is a solution, which we also call a homogeneous mixture of that substance, acetic anhydride, dissolved in water. And so she's measuring out 6 milliliters of the acetic anhydride, and she's going to just simply mix it in with the 3 grams of salicylic acid. And then to make the reaction go fast, she's going to add her acid catalyst. And she's just adding several drops of the acid as a catalyst and then mixing. And then she's going to go through some filtration steps in order to separate the aspirin product from the other side product, which is acetic anhydride. And so if you want to watch the rest of the video, please feel free to do so. So now we're going to look at our balanced equation for this chemical reaction that we just saw. And so the salicylic acid is C7H6O3, added to the acetic anhydride aqueous solution, which has the formula C4H6O3. Those two react with your acid catalyst being used. And for chemical reactions, if there's a catalyst involved, you actually put it on top of the arrow, because a catalyst is not a reactant because it doesn't get consumed in the reaction process. The catalyst will remain as its intact self and therefore can be used over and over again in the process of the reaction. And so the catalyst is usually written on top of the arrow to specify that it's not a reactant, nor is it a product. Our two products of this reaction are our aspirin, which is acetylsalicylic acid, and a side product called acetic acid, which is a weak acid. And now you also see the molecular structures for each reactant and each product drawn. And you also have some numbers down here. 138.12 grams per mole is the molar mass, which is the total mass for that compound, salicylic acid. The other reactant, acetic anhydride, has a molar mass of 102.09 grams per mole. You also see another number down here for acetic anhydride, and this is the density. Acetic anhydride has a density of 1.08 grams per milliliter. And then we're also given the molar mass for our solid product, aspirin, and the molar mass as well as density for our aqueous solution of the other product, acetic acid. So in the video, 3 grams of salicylic acid was mixed with 6 milliliters of acetic anhydride. So now we're introducing two new conversion factors, density and molar mass. Density is the amount of grams of a substance per milliliter. So you can see the units for density, grams per milliliter. Molar mass is the amount of grams of a substance per mole. The units for molar mass are grams per mole. So therefore, I can convert between grams and milliliters by using density, and I can convert between grams and moles by using the molar mass. And so we'll draw us a little flow chart here. So if I want to convert grams to moles, I divide by the molar mass. So I take grams, divide by the molar grams of that compound, divide by the molar mass of that compound, and I convert the grams to moles. And I can also go in the opposite direction. If I know how many moles of a compound that I have, I can convert those moles to grams by multiplying by the molar mass. So I can also start with grams and convert those grams to milliliters by dividing by the density. And then, of course, I can go in the opposite direction. If I know milliliters, I can convert the milliliters to grams by multiplying by density. So density and molar mass can be used as conversion factors to convert between grams and milliliters, or milliliters to grams using density, or convert grams to moles, or vice versa, moles to grams, by using the molar mass as a conversion factor. So a general formula for density is mass divided by volume. Now you can see density in different reference materials online or in textbooks. Most of the time you'll see density represented in units of gram per milliliter, but sometimes you'll see it represented as grams per cubic centimeter. And so 1 milliliter is the same thing as 1 cubic centimeter. So density units of grams per milliliter means the same thing as grams per cubic centimeter. A milliliter and a cubic centimeter, or centimeters cubed, means exactly the same thing. But in other textbooks, you may see density in units of grams per liter, especially when referring to specific substances like gases. But grams per milliliter is the more popular unit, especially when it comes to liquids and aqueous solutions. And so in our example of synthesis of aspirin, we've got grams of the salicylic acid reactant, but we have milliliters of the acetic anhydride reactant. So we need both of them to be in grams. So we need to convert the milliliters of acetic anhydride into grams. So our first calculation is to calculate the grams of acetic anhydride that we used. We used 6 milliliters. So we need to convert the milliliters to grams. So our rules for converting, our conversion factor is, of course, a fraction. The unit that we want to get rid of is milliliters. So we put milliliters in the denominator. The unit that we want is grams. So we put that in the numerator. And our little flow chart tells us if we want to go from milliliters to grams, we need to multiply by the density. And the density for acetic anhydride is 1.08 grams per milliliter. So we do our multiplication. 6 times 1.08. We get 6.48. Proper significant figures. .5 grams. Remember, density is a conversion factor. It's an exact number. The 6 milliliters is what the scientists measured out. So you always base your answer on the number of significant figures that the measured quantity has, and that's 2. The second calculation is we need to calculate the theoretical yield in grams of our aspirin product. So what the theoretical yield is simply a prediction of how much product, in this case aspirin, that we should produce in a perfect world. And it's going to be based on the starting mass of the limiting reactant. So the next question you have to ask yourself, well, okay, in order to calculate the theoretical yield then of my aspirin, how much aspirin should I make if I use 3 grams of salicylic acid and 6 milliliters, which is equivalent to 6.5 grams of acetic anhydride? How much aspirin should we be producing? Should we be producing 3 grams or 6.5 grams? Or something in the middle, or something less than 3, or something greater than 6.5. How much aspirin should we expect in a perfect world to produce based on the starting mass amounts of each reactant? And so no reaction is going to be 100% perfect. There's always going to be human error. No one's perfect. There's always some potential error in equipment. You know, your balance, is it perfectly calibrated? Are your filtration devices working optimally? Did you spill a little bit of your aspirin product during the process? So all those things, human error, equipment error, that causes you to not be in that perfect world situation. So what you actually produce is always going to be a little bit less than your prediction, which is your theoretical yield. So your actual yield is always going to be a little bit less than your theoretical yield. And that's normal because, hey, it's not a perfect world and there are no perfect people. There's always going to be some mistakes made. There's always going to be room for error. Okay? So to calculate the theoretical yield, the theoretical yield is always going to be in moles. So how many moles of our acid, of our aspirin, how many moles of our aspirin product do we expect to produce based on the starting, and let me correct this, the starting moles of the limiting reactant. Well, we know how many grams of each reactant we started out with. 3 grams of the salicylic acid, 6.5 grams of the acetic anhydride. So what we need to do to calculate the theoretical yield of how much product we expect to produce in moles, we need to convert the grams of each reactant to moles by using molar mass. Remember our little flow chart. To go from grams to moles, you divide by the molar mass. And so we're going to take the grams of each reactant. Our first reactant was the salicylic acid. We had 3 grams of it. And we're going to divide this 3 grams by the molar mass of salicylic acid, 138.12 grams per mole. Remember, grams is what we're getting rid of. So grams go in the denominator. We want to convert the grams to moles. So moles, and I always abbreviate mole, M-O-L. So moles go in the numerator, and we see that our grams cancel. So we do our math, 3.0 divided by 138.12. We get 2.17 times 10 to the negative 2 moles, and I'm going to abbreviate salicylic acid, SA. And then for our acetic anhydride, we started out with 6.5 grams of it. So we need to convert the grams to moles. So grams go in the denominator, moles go in the numerator. The grams cancel each other out. And the molar mass of acetic anhydride is 102.09 grams per mole. So we do our math, 6.5 divided by 102.09. We get 6.35 times 10 to the negative 2. Moles of acetic anhydride, which I'll abbreviate AA. So after you calculate the number of moles of each reactant, then you can determine the limiting reactant. The limiting reactant is going to be the one that's the smaller molar amount. So when you compare 2.17 times 10 to the negative 2 moles of salicylic acid with 6.35 times 10 to the negative 2 moles of acetic anhydride, you start out with a smaller molar amount of the salicylic acid. So it is your limiting reactant. And therefore, the acetic anhydride is your excess reactant. And so therefore, looking at our balanced chemical reaction again, you notice that there aren't any coefficients in front of each reactant or each product. So just as when there's no subscript in the formula denoting how many atoms, then it's understood that there's just one. Same thing for coefficients in front of a reactant or a product in a chemical reaction. If there's not a coefficient, then it's understood to be one. So what our balanced chemical reaction is saying is these coefficients the coefficient represents the stoichiometric molar amounts of each reactant and product. So it's a relative amount of each reactant and product that's in your balanced chemical reaction. So what this balanced chemical reaction for the production of aspirin is saying is that for every 1 mole of salicylic acid and 1 mole of acetic anhydride that you react together, you're going to produce 1 mole of aspirin, which is acetylsalicylic acid, and 1 mole of acetic acid. So your ratio of your limiting reactant, which is the salicylic acid, to our product of interest, which is the aspirin, is a 1-to-1 molar ratio. For every 1 mole of salicylic acid that reacts, 1 mole of aspirin is produced. So, with that being said, the theoretical yield then of aspirin is going to be the same as the limiting reactant molar amount. So because we start out with 2.17 times 10 to the negative 2 moles of our limiting reactant, we're going to be producing our aspirin product. We're going to be producing 2.17 times 10 to the negative 2 moles. But for theoretical yield, we want to know the amount in grams. Because in our labs, we don't have mole balances. We have mass balances in grams. So we need to know how many grams of product we should expect. Because at the end of the reaction, you want to weigh actually how many grams of the aspirin did you produce, and then compare that to your theoretical yield in grams. Okay, so we got to take our theoretical yield in moles for aspirin and convert it into grams. And going back to our flow chart, to convert moles to grams, you multiply by the molar mass. And the molar mass for aspirin, 180.16 grams per mole. So we're going to take the moles of the aspirin that we should theoretically produce based on the limiting reactant moles. You're not going to make any more product than the amount of the limiting reactant that you start out with, because it's the limiting reactant that determines how much product you make, not the excess reactant. So the limiting reactant limits the amount of product that's formed. So however many moles of your limiting reactant you start out with, you're going to produce that same number of moles of product. But the key is you got to convert the moles of that product to grams to get the theoretical yield by multiplying by the molar mass. So we want to get rid of moles this time. So moles go in the denominator. We want grams, so it goes in the numerator. And so we put in our molar mass, and that was 180.16 grams per mole for the aspirin. So the moles cancel. You do your multiplication, 2.17 times 10 to the negative 2 moles. Multiply it by 180.16. You get 3.91 grams. That is our theoretical yield. In a perfect world, that's how much aspirin that the scientist in the video, that's how much aspirin that she should be producing. So that's our theoretical yield. And so I'll just rewrite that calculation here. So we actually already answered question 3. So that is our theoretical yield. So that's how much we expect in a perfect world that we should be producing. So the limiting reactant, we've already answered that question. It's the salicylic acid. So in the video, if we would have continued to watch the video, we would hear in the video and see in the video that what was produced, and then we want to follow our significant figure rules. She started out with 3.0 grams of the reactant, and so therefore our theoretical yield, we only need 2 significant figures, so 3.9 grams. But what she actually produced was just 3.1 grams. So her percent yield is going to be equal to what she actually produced, the actual yield, divided by the expected yield, which we call our theoretical yield, times 100. So her percent yield is going to be 3.1 grams divided by 3.9 grams times 100. Which is 80%. So she actually made 80% of what was expected, which is not a bad yield, 80%. And note I have 2 significant figures in my answer. And so lots of states, including Tennessee, have emission standard requirements. And before you can renew your registration on your vehicle, you have to get an emissions test to make sure your engine is working properly. And so gasoline is made up of hydrocarbons. The major one that makes up the greatest percentage of the component of your gasoline is octane. So if you have 91 octane rating gasoline in your vehicle, that means your gas contains 91% octane. The other 9% is other stuff like heptane and other chemicals. So octane is a hydrocarbon with this formula, C8H18. So octane reacts with oxygen and you produce CO2 in water. So here's our balanced equation. Now, some people just do not like to have a fraction in their balanced equation. And it's perfectly okay to have a fraction or a decimal in your balanced equation. But some people just don't like the way it looks. And so if you don't like the way that looks, one way you can get rid of the fraction is by multiplying every coefficient. And remember, we said if there's not a coefficient in front, it's understood to be 1. You can get rid of that fraction by multiplying every coefficient in the balanced equation by 2. So if I multiply each coefficient, including the 1, in front of C8H10 by 2, this becomes my balanced equation. Multiplying 25 halves times 2 gives you 25. And now that gets rid of the fraction. Either one of these, both of these are considered correct. So either one is acceptable. And so one thing that the emissions test analyzes is the amount of carbon monoxide, CO, that's coming out of your tailpipe, in addition to some other air pollutants like nitrogen oxides, and also how much CO2 is coming out of your tailpipe, because it's a greenhouse gas that contributes to climate change. So if your engine is performing efficiently, then you should get a passing emissions test. But if your engine is not performing optimally, you may fail your emissions test and may need to take your car in for servicing for things like a tune-up. And so this little figure here is a copy of an emissions report, and it shows the amount of carbon monoxide in grams per mile that are generated from the exhaust. And so on the left-hand y-axis, you have the amounts in grams per mole, and then on the right-hand side, you have the miles per hour. Okay, and so therefore, you can see that the amount of carbon monoxide that is emitted in grams per mile, which is the red graph, and then how much CO is emitted as you increase your speed from 0 to 60. That's the blue graph. So you can see as you go up to higher speeds, the amount of carbon monoxide also increases correspondingly with increased speed. And the faster that this vehicle goes, you can see the amount of carbon monoxide increase above the green line. And that green line is the standard line. That's what's acceptable. So you need to be under that green line to have a passing emissions test for carbon monoxide. And so this vehicle did not pass based on carbon monoxide and also nitrogen oxides. You can see they're above that green standard line. As far as emissions of carbon dioxide, CO2, there aren't any standards set. I know as of 2016, there wasn't. So you don't see a green line on that graph. But you can see, again, as the speed increases, so does the amount of CO2 that comes out of the tailpipe. So therefore, this vehicle would not pass the emissions test because as you go above 40 miles per hour, you can see that the amount of carbon monoxide and the amount of nitrogen oxides goes way above the green line, what's considered standard. And so if you want more information on the standards that the EPA has set, you can visit that website. And so we talked about those 6 main dangerous air pollutants. That includes SO2, sulfur dioxide, nitrogen oxides, and also carbon monoxide, ozone, lead, and particulate matter. All of those pollutants, those 6, are called primary pollutants. Now, there are also secondary pollutants, like SO3. And so secondary pollutants are formed from primary pollutants. So sulfur trioxide, SO3, is a secondary pollutant, and it's formed from SO2. So here you have sulfur and you have O2. They react to form SO2. And so the source of this sulfur mainly is from burning coal, but also volcanic eruptions are a source of sulfur. And so this reaction, you have S plus O2 producing SO2. And then the SO2 that is formed will react with oxygen in the air. And that's how SO3 gets formed. And of course, we've got to make sure our reaction's balanced, and it's not. We've got 3 oxygens on the right, but we got 4 oxygens on the left. And so therefore, to balance, we'll put a 2 coefficient here, giving us a total of 6. 2 times 2, 4 plus 2, 6 oxygens on the left, and then putting a 2 coefficient here gives us 6 oxygens on the right, and our sulfurs are also balanced. We've got 2 on each side. So that's how SO3, a secondary pollutant, is formed. It's formed from SO2, which is a primary pollutant. Now, sulfur trioxide, not only is it an air pollutant, but it can cause other problems. It can then go on to react with water in the atmosphere to produce an acid called sulfuric acid, which is bad because it contributes to acid rain. But since 1985, there has been a 55% reduction in SO2 emissions in the United States. And therefore, there's less SO2 in the atmosphere that can react with oxygen and form SO3, and therefore less SO3 that can further react with water to form sulfuric acid. H2SO4. That's the formula for sulfuric acid, which is a major component of acid rain. So when that sulfuric acid forms up in our atmosphere, it falls back to the earth, and that's what we call acid rain. And now carbon monoxide is another primary pollutant that we talked about. And it comes from automobiles exhausts when there's incomplete combustion of the hydrocarbons. And then we have our nitrogen oxides, NO and NO2, which are primary pollutants. And those pollutants come from hot automobile engines. And so it's formed inside of a hot automobile engine because the heat from the automobile engine actually acts as a catalyst. So we have our nitrogen, N2, our oxygen, O2, and those are naturally, of course, present in the air. But in an automobile engine, which is under extremely hot conditions, it acts as a catalyst and causes the nitrogen in the air to react with the oxygen in the air to produce nitrogen monoxide. And then the nitrogen monoxide compounds will go on and react with oxygen in the air to form your nitrogen dioxide air pollutant. So NO2 is a brown gas that gives smog its characteristic brown color. And so we wrote these two reaction steps, and this is called a reaction mechanism. So it's called a reaction mechanism because there's more than one reaction involved in order to get your final product, which is NO2. It takes two steps. The first step is your N2 plus O2. And then your second step so therefore we've shown the particulate view of this mechanism by showing the models. And then this is the symbolic view of those two steps and the mechanism. Now, NO2 is also produced by another air pollutant, which is a primary pollutant, ozone. So nitrogen monoxide that's produced by nitrogen and oxygen reacting in a hot car engine. The nitrogen monoxide normally reacts with oxygen, but if there's ground level ozone, O3 present, then the nitrogen monoxide will react with the ozone and that also produces NO2. So this is an alternative way of producing NO2. It's from the nitrogen monoxide reacting with O3 instead of O2. Now, we said that, for instance, if you have 91 grade gasoline in your car, that's 91 octane rating, meaning you got 91% octane in your gas. The other 9% is other stuff. Some of that other stuff can be what's called volatile organic compounds, VOCs. So VOCs emitted from vehicle exhaust, they can also form nitrogen dioxide. And so this involves another reaction mechanism. So your VOC, your volatile organic compound, it will react with what's called a radical. Radical compounds are known, and we'll learn more about this in a chapter coming up here. They're known by having a little single electron represented as a dot next to them. And this is a hydroxide, OH. So it's called a hydroxyl or hydroxide radical. And it's going to produce an intermediate compound that we'll just call compound A. And then compound A reacts with oxygen in the air to form another intermediate compound that we'll call A prime. And then A prime reacts with NO we'll rewrite this one. So A prime then goes on to react with the nitrogen monoxide that's formed from N2 and O2 reacting in the hot car engine and produce another intermediate, A double prime plus the NO2 product. So that's another different reaction mechanism that takes place inside of the hot car engine that produces NO2 exhaust as well. So you can see that there are 3 different routes to producing nitrogen dioxide, which is a very serious air pollutant. And it's what makes photochemical smog have the typical brown color. So how can we reduce all these dangerous air pollutant emissions coming from our automobiles? Well, one way that we've been able to do that and therefore improve air pollution quality in the various cities in the United States is the catalytic converter. Catalytic converters, they reduce the amount of carbon monoxide in the exhaust because the catalytic converter has catalysts inside of it. And these catalysts, they catalyze the combustion of carbon monoxide to carbon dioxide. So that's why your catalytic converter in your car is so important. It takes the carbon monoxide that's being produced and converts it to carbon dioxide. Newer designs of catalytic converters can also limit the release of the nitrogen oxides by reducing them to nitrogen gas and oxygen gases. So therefore, the catalytic converter is a very important tool in that has helped us improve the air quality in the United States. Now that most dangerous air pollutant as far as to the human body, particulate matter, its sources come from fireplaces, wood burning stoves, wildfires, construction sites, diesel engines, and of course, volcanic eruptions. Now, ozone can be considered a primary pollutant, but it can also be a secondary pollutant that gets produced from oxygen. And so the EPA has a website called AirNow, and it provides you daily information regarding particulate matter and ozone concentrations for local regions in the United States. And so here we see a map of Southern California, and it shows that ozone concentrations tend to reach a peak around mid-afternoon, I guess during high traffic times. And then those ozone concentrations tend to drop overnight. And so sunlight is used as a catalyst to produce ozone from volatile organic compounds and nitrogen oxides. So that's why you see a drop in the ozone concentration at night versus middle of the day. So that website is airnow.gov. So if you want to know what's the ozone concentration and the carbon monoxide concentrations in Chattanooga today, you can go to that site and it will tell you. So unlike nitrogen and sulfur oxides that are direct pollutants, ozone is mainly considered a secondary pollutant. But ozone is listed with those 6 most dangerous air pollutants. But of the 6, it is the secondary pollutant. The other 5 are considered primary pollutants. So ozone as a secondary pollutant is produced from nitrogen dioxide that's formed in the hot engines using sunlight as a catalyst. You produce nitrogen monoxide, and you got free atomic oxygen. It's not O2, it's just one single oxygen atom. And it is very reactive. It doesn't like to stay by itself. Because in nature, it's not normally by itself. So it's going to react quick with oxygen O2 to produce ozone. So the hot car engine producing nitrogen monoxide, and therefore this atomic oxygen being very reactive will react with oxygen O2, and that's how you get the ozone production. So the ozone secondary pollutant that's found in the troposphere, it is a direct result of automobile engine exhaust. In the stratosphere, that's where ozone belongs. It keeps us safe from cosmic solar rays because it destroys the strongest UV radiation before it reaches the Earth. But ozone in the troposphere is a secondary air pollutant. So what about indoor air pollution? Everything we've been talking about so far is outdoor air pollution. Should you be concerned about indoor air pollution? Well, absolutely. So when we think about indoor air pollution, you want to think about things like your paint. If you're painting your the inside of your house, do you have proper ventilation? Also, what's in the paint? Most paints have volatile organic compounds and maybe other chemical compounds that may cause health issues if you're not painting in a well-ventilated area. So ventilation is very important. Also, burning a candle or burning an incense. You may not even think about air pollution when you do those things. And again, it's important to read the labels that's on that incense or that candle and to make sure there aren't any dangerous chemicals that may break down to become air pollutants. So these can be air pollutants depending on what types of chemicals that they contain. And another dangerous air pollutant that a lot of us may have heard about is radon. And most electrical products tend to be a source of radon. And also making sure your furnace, things like that, making sure they're working properly is another good way to reduce the amount of indoor air pollution that you have. Because just like an automobile engine that's not working correctly, if your furnace is not working correctly, you can have some incomplete combustion of the natural gas if your home has natural gas for its heating. And so therefore that can cause carbon monoxide to be produced instead of CO2. So making sure your electrical devices and appliances and your furnace and all those things, making sure they're working properly is another good way to help prevent indoor air pollution. So the way forward, sustainability. So the EPA Design for the Environment program, they initiated what are called green chemistry programs. Green chemistry is the concept of reducing pollution through the design or the redesign of chemical processes. How can you change a chemical process, a chemical mechanism of reactions so that you produce less harmful air pollutants? So green processes, their goal is to reduce air pollution, use less energy, create less waste, use fewer natural resources, and where possible, use renewable resources. So some examples include plastics that are synthesized from plant-based sources and other renewable sources rather than the typical fossil fuel-based precursors that are used to make plastics. Also paints, make sure they contain fewer VOCs. Cheaper and less wasteful ways to produce consumer products. Limiting or eliminating the use of organic solvents, and removing arsenic from touchscreens of portable electronic devices. And I had no idea in the beginning when they first started making the touchscreen style cell phones that there was arsenic in that material that makes the touchscreen. And since then, the EPA has ordered that no touchscreens are made from arsenic anymore. But you think about it, when little kids play with their parents' cell phones, little kids put everything in their mouths. And so knowing that your touchscreen does not have arsenic in it is a very, very positive thing. And so no matter what your philosophy is about the EPA and government regulations, I like to think of them as someone having my back, watching out for my best interest. Because a lot of these things we just don't in our daily lives. Even if you are a science major or a scientist, or still in your busy, hectic, everyday lives, a lot of this stuff you don't think about or even ask questions about. But it should be good to know that here in the United States, we have an agency like the EPA that is looking at things like that, whether or not there's arsenic in touchscreens of cell phones, things like that to help keep us safe. And so, of course, there are always debatable topics, no matter what. And good, healthy debate is a good thing. But overall, I know myself, both as a scientist and as a citizen, I do appreciate the work that the EPA does. And regulations aren't always a bad thing. They can be a good thing. Because I know my little godson plays with my cell phone all the time, and he puts everything in his mouth. So it's good to know there isn't any arsenic in the touchscreen of my cell phone. That brings us to the end of chapter 2. So we're going to try to complete chapter 2 by Wednesday, the 10th. If we don't, we may have a little bit of it to finish off in class on Monday, the 15th.